on exponential functions. The definition for an exponential function is in the middle of page 422. It says an exponential function f with the base b is defined by f of x is equal to b to the x. Again, what I want to point out to you is that it's an exponential function because there's a variable. B is just any real number. Okay? So b is going to be a number, so it's going to be something like 2 to the x or 1/2 to the x or whatever. It is on page 422. No problem. A lot of times they do use the variable b for a number in these kind of textbooks. The other thing that b has to be a real number, and it also needs to be positive. So we're not going to be talking right now about -2 raised to a power, because that's not always a function. If you've got a negative sign, it kind of does weird things. Okay? So any questions about the definition of an exponential function? All right, so Objective 1 in this section wants us to be able to evaluate exponential functions. In other words, I just want you to understand the concept of what's going on. We've had a lot of different things where we've had things raised to powers, but usually our exponent's a number, right? So it just looks a little bit different to us. So one thing we want to talk about first is we want to talk about how to graph this. So check point 1, while we're talking about how to evaluate these and what we're going to do. One of the ways that we can do that is by graphing it and then looking at the value. So they tell us that they want us to graph f of x being equal to 3 to the x power. Okay, so we set ourselves a table of values. All right. This is an exponential function, yes. Okay. So let's put in a 0 for x. What's 3 to the 0 power? No. Anything to the 0 power is 1. Good. Okay. What? That's just a definition that you need to memorize. Anything to the 0 power is 1 for the rest of your life. If I have an exponent of 1, that's 3 to the first power, which is 3. And if I have an x of 2, that means 3 to the second power, which is 9. But we also need to check for the rest of our domain, because we can also have negative numbers, right? Negative numbers. So if I have -1 for my exponent, that's 3 to the -1. Does anybody from last year remember what something to a negative exponent means to us? Or how do we work with that? Puts it in the denominator. So this is 1 over 3 to the first. Negative exponents mean that it's the inverse. Okay? Reciprocal is what it really means for this case, because it's the multiplicative inverse, which is the reciprocal. Okay? So the negative sign tells me that I need to use the reciprocal of that. So if I had a -2 for my exponent, that's 3 to the -2 power, but that turns into 1 over 3 to the +2 power. But what's 3 squared? 9. So it's actually 1 over 9. B does have to be positive. X does not. Okay? The number right. Yeah, because what we're varying this time is the exponent, not the base, like we've always done before. Are we good? All right. So let's just draw that and plot these points, because we can always plot points and graph something, right? Okay, well, I mean, you just go, this says to go left or right 0 and go up 1. Okay. Oh, yeah, for the lines, linear equations, and slope and stuff, yep. So we'll work on that some more. And then the next point is 1, 3, so I go over 1 and up 3. And the next point is 2, 9, so over 2 and up 9. And then at -1, so I go left 1, and then I go up a third. And at left 2, I'm only up a ninth. So can you see that this exponential function is going to look something like that? So now we've evaluated this f of x at several different x values, right? Because this is f of 0. This is f of 1. Isn't that what that means? Right? That's what we've done, is we've been evaluating this function. And once we evaluate it and find the ordered pairs, then I can actually plot those and draw the graph. Or, like we did earlier in the year, if I'm given the graph, from the graph I can evaluate those points, right? Yes? All right. Any questions about that? That is the basic shape of an exponential function. So it's got a horizontal asymptote on one side, and on the other side it shoots off to a positive infinity or a negative infinity if it's got a reflection, because we have all the same transformations for these exponential functions that we had for quadratics and everything else. We can reflect it across the line, y equal x, reflect it across the line, the y-axis. We can stretch it out, we can shrink it down, we can move it left, we can move it right, move it up, we can move it down, right? All those same transformations that we had before, we have now. But that's the basic shape, okay? And just for FYI, and I don't know if they talk about that in this book so much, but do you remember that your exponential function parent function was y is equal to 2 to the x? That's your parent function, remember? Because 2 is the smallest number besides 1, and 1 doesn't do anything, it's just flat. Because 1 raised to any power is still just 1, so it's not really a curve. Okay? So, checkpoint 3. Doing some more with this graphing. Says f of x is equal to 1 over 3 raised to the x power. So, and they have a note there beside it. They want you to notice something. What do you know about 1 over 3? How can I write that with a negative exponent? How about just 3 to the negative 1? Right? I just take whatever's in the denominator and I write it to the negative 1, and that's the same thing. That's equivalent. You take whatever exponent's in the bottom. Right now it's an understood 1, and just make it negative. Okay? So you can go back and forth either way. And so that means that if that's the case, then I can take my f of x, and instead of writing it as 1/3 to the x, that's the same thing as 3 to the negative 1 to the x, right? If we say 1/3 is equal to 3 to the negative 1, I can interchange those. What do I know about taking a power and raising it to another power? What do I do to the two exponents? What's that rule of exponents? Not add them, multiply them. If I'm taking one power and raising it to another power, I multiply. If I'm taking two bases, like bases, and multiplying them together, that's when I add their exponents. Okay? So that's the same thing as 3 to the negative x. So they do want you to notice that 1/3 to the x is the same thing as 3 to the negative x. Okay? Now what did negative signs do to us before? They reflected it, right? Sometimes they reflected across the x, sometimes they reflected it across the y, but those were reflections. Anytime I had negative signs involved, other than when I was adding or subtracting a negative, but when I multiply by a negative like that. Sorry, y'all, my throat is killing me. Alright, so let's look and see what happens with this. Particular function. Yes, I just pick some x values because I'm just plugging it in as an exponent, and I find the y to go with it. That's exactly how I'm doing it. I'm just evaluating them. And so, again, if I have an x of 0, anything to the 0 power is 1. So can you see, unless you add or subtract something, you're really going to always have that point, right? Now, if I take my positive 1 and my positive 2 that I used before, this time when I put that in, that becomes 3 to the negative 1, right? And so it goes back to that 1/3. Or you can think of it as 1/3 being raised to the first power. I just want to show you that these numbers are going to be the same from the last graph that we just did, right? Except what? At 2, it's going to be 3 to the negative 2, which will be 1/9. And before, positive 2 gave me a positive 9. Do you see what we've done? And now we've got a negative 1. Now negative 1 is like 3, right? Because 1/3 raised to negative 1 is going to flip 1/3 upside down and make it 3/1. And then negative 2 is going to make it 9. Put some space up there. So I've got this 0.01 again. At 1 I'm at 1/3, and at 2 I'm at 1/9. At negative 1 I'm at 3, and at 2 I'm at 9. So what is the difference between this graph and the first one that we did? Reflected it where? Across the y-axis, not the x-axis. Okay? Any questions about that? So if you will look at the bottom of page 425 in the blue box, there is a summary there of all the characteristics and all the things that can happen with these graphs. Inequalities. So let's just talk about those inequalities just for a minute. Number 1 says the domain's always going to go left forever and right forever, so the domain's going to be all real numbers. But see how the range is always kind of cut off? This one starts at 0 and goes up forever. So there's going to be a definite range, but the domain for exponential functions, for the most part, is all real numbers. Then on number 2, what it's saying is that they all pass through this 0.01. Unless there's some number added or subtracted to the equation, if it's just a number raised to the exponent, it's just going to pass through this 0.01. Okay? It says if b is greater than 1. Remember, we said b had to be greater than 0, but it's saying if it's a number bigger than 1, then f of x equal b to the x is a graph that goes up to the right and is increasing. So remember it was this one. Right? Because 3 is a number bigger than 1, so it's an increasing graph. So it's going to look like that. The next one says that if b is between 0 and 1, that's a fraction like 1/3. Okay? For it to say b is between 0 and 1 means it's a fraction or a decimal somewhere between 0 and 1. Top number smaller than the bottom number. Right? That's always going to be a decreasing function. It's always going to go this direction. It's always going to reflect it across that line the y-axis. Okay? Which is x equals 0. Number 5 says that f of x equal b to the x is 1-to-1. Does anybody remember what the term 1-to-1 meant? That it is a function and its inverse is a function. Right? Okay, so can you see it passes the vertical line test and it also passes the horizontal line test. So it's 1-to-1. Okay, and then it says that we approach but do not touch the x-axis. So that makes this x-axis here remember what we call that when it gets close to something but doesn't touch it? An asymptote, and it happens to be a horizontal asymptote. Okay? We good? All right. On page 426, it starts talking about transformations. Just like I told you, every other transformation that we've done with quadratic equations, everything else that we've done, apply to these exponential functions too. So if you will look, what are they doing to the equation in the first box there? My equation is f of x equal b to the x, right? They added a vertical shift. And how did they do that? By subtracting or adding c. What does c stand for? A constant. It's just a number. So if they just add or subtract a number out behind the exponent, then that's going to shift it up or down. If they added it, it's going to shift. I'm on the top of page 426. Inside the box. Yeah. Okay. So everybody see it? You remember seeing this notation before, right? We did a lot of this last year in Algebra 2. Well, for some people it was last year. Okay, remember that now? All right, and look at the next one. This is a horizontal. It's a left or right shift. This time, where did they add the number or subtract the number? With the exponent. And remember that if it's with the x, it's kind of like an understood set of parentheses. They don't put the parentheses around it, but if it's in the exponent, if you were going to type it in, you'd have to put it in parentheses, right? And if it's inside the parentheses, what happens to the movement? So it's the opposite of what you think. So if you're adding a number, you're going to move to the left, and if you're subtracting a number, you're going to move to the right. Good. All right. The reflections. Now, I want you to notice this because we talked about this a second ago. So I want to just make sure that you understand what this means. That does not mean that b is a negative number. Everybody hear what I just said? This is not the same as that. Okay? We've talked about that before with the square stuff, right? Y'all be doing stuff like this? Right? So, we're not saying that b is negative. We're saying we've got b, we're raising it to a power, and then we're going to take the answer and make it negative. So every y value I get back is going to be a negative number, is what this says right here. Everybody get that? We're going to raise order of operations. So I'm going to take this number that b is, and it'll be a positive number. I'm going to raise it to an exponent. Then, after I do that part, then I'm going to make it negative. Okay? That reflects it across the x-axis. That's going to put all of it down on the bottom now, right? Instead of all... Right. order of operations since I do exponents before I do any multiplication. Okay, good. And then the one that we've already looked at, the b to the negative x, reflects it across the y-axis, right? We looked at that one already. Okay. A vertical stretch or shrink, remember that's when you multiply by some number. So it might say, might have something like that, where you've got your base is being raised to a power, but it's being multiplied by a number in front. Okay, that's a vertical stretch or shrink. And then you can do a horizontal stretch or shrink if you take the exponent and multiply it by a number. So you can have like 2 to the 2x. We did this exact same thing towards the end of the year last year. Matter of fact, I took a lot of the material from this book because the way that the material we were using in Algebra 2 stretched it out over too long a period and we didn't have enough time. So actually this should look real familiar. I didn't pull these books out for y'all, but I used the material out of here. Okay? All right. Any other questions? So on checkpoint 4, they want you to just use that idea of transformations to decide what this is going to look like. So it says they want us to do that g of x is 3 to the x minus 1. Now, we've already been on all of our other checkpoints looking to see what the graph of 3 to the x looks like, right? So we know what 3 to the positive x looks like. Set this point 0, 0. It's a third, a ninth, 3, and a 9. Right? So that's y is equal to 3 to the x, or f of x is equal to 3 to the x. Now I want you to think about it for a minute. Look at what the equation looks like. Look back in that table that we just looked over and tell me in words, how do you think this graph has changed? It's a horizontal translation. What does that mean, though? Am I going to move it left, right, up, down, shrink it, stretch it? We're just going to take that whole thing, just like it is, and shove it which way? To the right. How many units? Just 1. Okay? So we're just, every one of these would just be moved over just one place. Let me do that in a different color so you can see it. I don't remember which color y'all said y'all can see better than the other ones. Does red look a lot different than black? Okay. Okay, so that's the new one. It's just a horizontal shift 1 unit to the right. So remember that when you start doing these with those translations, they just expect you to just take the points and just move them over. They don't expect you to go through the process of substituting the number in and working the whole thing out again algebraically. You can. I'm not saying it's wrong. I'm just saying that's what they expect you to do on the homework assignment. Okay? You might want to mark that page so that you remember. Objective 3 in this section is that they want us to be able to evaluate functions with base e. Well, it helps if I can spell. Okay, so the base is e. Well, wait a minute. Didn't I say that the number that I'm raising the exponent to has to just be a number? Can't be a letter. Somebody talk to me about why this is okay and why is it even in this darn section. This section, we said the base was going to be a number raised to a variable. I got 2 variables now. I got a variable being raised to a variable. Why is this okay? E is what? E is not a variable, is it? No. E is a number. Yes, it's called, you knew that. Does anybody remember about what the approximation for E is? That's exactly right. It's 2.718. Keeps going forever and ever. Yeah, something like that. All right. So, it's the number that's a little bit bigger than 2. It's between 2 and 3. Does anybody remember why they use a letter for it? It's just like pi. They actually found, this is one of the irrational numbers that we have that they found in nature. It's used for population growth and money a lot. There's an E to the X button. Yeah, it's above the LN button. If you look over there on the, it's in a couple of places. It's on the very far left-hand column. It's there, and then there's also another one over on the right-hand side. I mean, over to the right from that. So there's a couple of different places where you can use the E. Okay? So E is a number. It's not a variable, and that's why it goes in this section, because it's a number bigger than 1. Right? So all the same rules apply to this as what we had before. So if we look at one of these population growths, let's see, checkpoint 6 is on page 428. It says the exponential function f of x is equal to 1066 e to the 0.042x, models the gray wolf population of the western Great Lakes. And x is how many years it's been since 1979. Did I say 1979? I think it says 1978, doesn't it? Yep. So it wants us to predict the wolf population in this area in 2012. Okay? So like I say, population growth is many times modeled with exponential equations for a period of time. And so what would we have to do here to be able to work this problem? How can we predict this wolf population using this model that we have here? Okay? So the first step is, I don't use 2012 for x, but I need to subtract. Okay, that'll tell me how many years it's been since 1978. So 34 years. 44? Wouldn't it be 34? Okay. So f of 34 is 1066 times e to the 0.042 times 34. So my problem here becomes putting it in the calculator, right? Because you do have to be careful. What do you have to make sure you do? Around what? All of the exponents, right? So you don't necessarily need these little individual ones. You could just put a times sign in between those two numbers. But make sure that you put both of the things that you want to multiply. Or just kind of work backwards and first multiply these two pieces for the exponent, find that answer, and then raise e to that, and then multiply it by the 1066. Okay, did you find the e to the x button? It's over on the very far left-hand side. So you'll type in 1066, you'll hit the e to the x button, and then open a set of parentheses and do the That'd be nice. So can I have 0.59 of a wolf? Okay, so how many, what would our wolf population be? Want to round it up to a 6? Okay. You like the 5? I don't care. All right. Yeah. That's right. That's because, see, you didn't put this all in parentheses.
Oh, you got a double parentheses above it? Oh, okay.
Either that or you can put don't put those little parentheses in there. And then it would have taken all of that as the exponent.
Okay.
Okay. All right. So, anybody got any question about this population growth? And truly, if you have a long range population growth, Devin, they actually have something called logistic growth, because what happens in a population is it doesn't keep increasing sharply like that. You know, after a while, when the resources start kind of dwindling down, you get this plateau, because in nature, it's really cool, most species besides humans have a survival instinct, and like they reabsorb their babies, or they don't have, you know, their bodies don't reproduce that particular year if there's a real tight condition where they're not getting any resources or anything. Well, I don't know about everything, but I do know that with rabbits they really do. If there's not enough food and water in the area, they may go ahead and they've done autopsies on them, and the babies are being reabsorbed into their systems. So instead of their bodies putting nutrients towards the babies, they pull it back out. So it's kind of cool the way nature, you know, takes care of that. All right. The last objective that's in this section, I want you to be able to use compound interest. There are two forms of compound interest that we're going to talk about. One is where it's compounded in a regular way, and the other is called compounded continuously. Now, what this compounding means, the whole idea behind compounding, for those of you who haven't messed much with the savings account ever, or had payments on something, the idea here is that when they do the interest calculation, they do it not just based on what you originally borrowed or originally put in, but they also pay you interest on your interest if you're talking about a savings account, or the interest amount actually goes down as you pay off a loan. So let's say you borrow $10,000. If it's compounded monthly, then at the end of the month, they take 10,000 times the amount of your interest rate, and that's what you owe then, and then they take your payment off of that. So like if you're making a $200 payment on a $10,000 loan, all of the $200 doesn't go, so you don't owe like $9,800 when you make that $200 payment, because some of that $200 paid off the interest that you were having to pay the bank for allowing you to use their $10,000. Okay? Y'all kind of understand that? Well, then let's do it the other way. Let's say that you start a savings account and you put $200 in there, and you get 5% interest. Okay? So at the end of the month, when they calculate your interest, you got, I don't know what, 5% of 200 would be? About 10 cents? Or would it be $10? I don't know. So you now got $210 in the bank. Well, at the end of the second month, they don't just give you that same $10 again, because you get 5% of the $210 that's in there now. Okay, so it's the same idea in reverse when you borrow money. Oh, yeah. Unless your mama gives you money. That might be the only person in the world that will give you money without doing interest. Yeah, because you very seldom get 5% interest. The kind of interest rate you get on savings account is usually like 0.04. It's not much. Yeah, as a matter of fact, I think that I have a savings account that my husband, who was killed, had started, and I just never have bothered to go up there and cancel it. It's got about $100 in it, and I think in the last quarter they gave me 2 cents for them having that money. That, you know, you just don't get a whole lot of money. You pay a lot when you borrow money, but you don't get much when you're saving money. Anyway, that's a whole nother lecture about how to manage your own money. But what I'm going to show you is the formulas that they use at the bank to calculate that stuff. Okay? Compound interest, like I say, it can be compounded in lots of different ways when they compound interest. They can compound it yearly. That means once a year they're going to figure the interest. They can compound it bi-yearly or semi-annually. Sometimes semi-annually is the way you'll see that more often. Semi-annually means they're going to do it twice that year. They could do it quarterly. What does that mean? How many times are they going to figure the interest? 4 times. Okay, quarterly they're going to do it 4 times, semi-annually 2, and yearly we're going to do it just once. That's called simple interest, by the way. It's just done yearly. And then we have monthly. So how many times would they figure the interest? 12 times. Okay? Good deal. Now, I will tell you that there's more money generated for you if it's a savings account and for them if it's a loan, the more times they figure the interest, because they're figuring the interest on interest that's already been figured. Okay? So a lot of times they use something that we call compounded continuously. If we sat here and we worked this out and we used the formula and we looked to see what would happen if we compounded it monthly or if we compounded it every 2 weeks or weekly or daily, you would see that the money kind of starts getting close to the same, but it creeps up just a little bit all the time. And so the limit of that is what we call compounding continuously. Okay? It's got a different formula, but it's the same idea. Okay? So there are 2 basic formulas that we're going to use. When they tell us it's compounded and they give us a definite number of times it's going to be compounded, then the formula that we use is that the amount in the account, A, is equal to the principal, which is how much we borrowed or how much we started saving just at the beginning. So A is the amount in the account right now, or the amount the account's worth right now. P is the amount that was originally put in. 1 plus the interest rate, which is designated as R, divided by N, which is the number of times it's going to be compounded, raised to the NT power. So you're going to need to write that formula down for yourself and write down what all the letters stand for. What is it? P is the original amount. That's a number 1. R is the interest rate, and it is the yearly interest rate. Let me go ahead and put that on there. in decimal form. Yep. N is the number of times the interest is compounded. And T is the number of years. T is the time and the number of years. Okay, so that's the one where if they tell me it's compounded monthly or semi-annually or weekly or whatever. If they tell me it's compounded continuously, then my formula is A is equal to P times E to the RT, where still P stands for the principal, the original amount, R still stands for the yearly interest rate in decimal form, and T still stands for the number of years. But all of this stuff kind of squinches together and just becomes E. And I could show you how. I think in the book they give you a breakdown on how it gets closer and closer to that. Yeah, it's like on the bottom of page 429. So if you want to look at that proof on the fact that that actually does turn into this, then you can. Yes, sir. In E. That's the idea here, is that the base is the population growth again. The population being your money this time. And it just turns, the more often you compound interest, the closer you get to that just being the number E raised to the rate times the time power. This is if they tell me it's compounded monthly or semi-annually or weekly or whatever. And this is when they tell us it's compounded continuously. Got it? So check point 7. Okay, they tell me that I've got a sum of $10,000 and I'm going to invest it at an annual rate of 8%. Okay. Find the balance in the account after 5 years. If A, we're going to use quarterly compounding. So if it's quarterly compounding, then I need to use this formula, that the amount in the account is equal to the principal times 1 plus n divided by r raised to the n times t power. Darn it. Not if it said compounded quarterly. No, you need to know that other one with the E in it, if it said it was compounded continuously. Okay? So I'm looking for the amount in the account. The principal is the original amount invested, so that's where the $10,000 goes. One's just 1. The interest rate in decimal form would be 0.08. If I'm compounding it quarterly, how many times a year did I say that meant? 4. And I'm going to raise it to the 4 times 5 power. Because it said after 5 years. Okay, so be very careful typing that into your calculator. You got your 10,000, you need to open a parentheses, 1 plus 0.08 divided by 4, close your parentheses, use your little housetop looking key, caret key. And 5 times 4, you can just go ahead and write as 20, hopefully. Right? Okay? So we have 14,859 and 7 cents, 47 cents. Okay. $14,859.47. Would, no, well, okay, if it was a loan, but they said this is a savings account and I'm investing it. So, okay. Yeah, nothing's paying 8% interest right now. You can forget that. All right. And then part B of this says, okay, well, what if we compounded it continuously for those 5 years? So if I'm compounding continuously, this is the one, Alexis, where I use this other formula. Or if it has any kind of compounding, if it says monthly, weekly, she's hungry, she's eating a quarter pounder. All right. Okay, so I've got 10,000, and then E, and E needs to be raised to the 0.08 times 5. Because you just take the annual interest rate, just like it is, times how many years. And let's talk about how much would be in that account if we compounded this continuously as opposed to quarterly. Okay? So as you can see, the more times you compound it, the more money you get. Not a whole lot more, but a little bit. Okay? Any questions? Wait a minute.